Hello everyone! So today I'm going to be doing another lesson on nuclear energy. Today is on fission and fusion. And I'm going to start with the main difference between fission and fusion in a very visual way. So in nuclear fission, what happens is that you have a large nuclei and it's going to be large and unstable. So it's going to split into two smaller nuclei, okay? And then when this happens, it releases a lot of energy. Nuclear fusion is kind of the opposite process, but it even releases more energy. So both release a lot of energy, it's just of the process is one opposite to the other. So with nuclear fusion, you have two smaller nuclei that fuse together and make a larger nuclei, okay? I'm going to tell you about both of them, but not so much the background information, a little bit more detailed than you would have learned about, you know, this fusion and fission and fusion in GCSE. But I will later on be doing one with not so much heavy stuff into it. Okay. So induced fission. So what happens is when I have a large nucleus, I can make it to undergo fission. So that means that I have a fissionable isotope and I'm going to bombard it with a neutron, and this is going to make that a very large atom that was already unstable, or nucleus that was already unstable, is going to split apart into two smaller fragments, okay? So it's like the example that I give in classes most of the time is like you full of shopping bags, and then you're really just holding on to the bags, just about holding it all together, and then someone is playing football, you get hit by the football, and then you drop the bags. It's the same thing. So you have a very large nuclei, something goes in, the nuclear just about gets it all together, something hits in, so it splits into pieces, so the different bags go in different directions. Then that fission neutron is still carries on and can make more fission events to happen. And then when you have the smaller nuclei, you also get two neutrons, one per nuclei that they are going to be emitted. So isotopes, they are going to be fissionable. They are uranium-23592 and plutonium-23994. So you can use them, and power stations use them, okay? Now the plutonium is actually an artificial isotope that is formed when I bombard the uranium with neutrons, okay? Now, the complete fission, for you to have an idea of the amount of energy I'm talking about, the complete fission of only 235 grams of uranium-235 is going to release about 10 to the power of 13 joules of energy. So 10 and then 13 zeros joules of energy, that's a lot, okay? Or 1 and then 13 zeros, sorry. So that's going to be about 1,000,000 times more than the energy that I release when I burn a similar mass of fossil fuel. So that's why people are using these isotopes in nuclear power stations, because it does give a lot of energy and it can meet the demands, the global demand that is increasing. Of course, there are problems with nuclear fission, and we are going to mention them as well, if not in this video, later on. There are many things that we need to be aware of and careful with, but that's the reason why they are nuclear fission reactors at the moment. Now, the thing about nuclear fission is, as I told you, you get a chain reaction. So you get one neutron, that produces the fission, and then this neutron is going to carry on. And then when you have fission, you get two more neutrons, okay? Two other neutrons, because each smaller fragment of a nuclei is going to give you a neutron. So every time that you get one neutron, you produce more fission that produces more fission, and so on and so on and so on. So this is called a chain reaction. Now, because each fission event is going to release two neutrons more, after n generation of fission events, then the number of fission neutrons that I'm going to have is going to be 2 to the power of n, okay? So this is how the chain reaction goes. And I actually have a video, which is not mine, which has a lab representation of nuclear fission. So I'm going to add it in the description. So the video shows lots of, I believe they are golf balls or ping pong balls. They are just about stable on top of mouse traps. and then they starts the, let's say, chain reaction, which is a representation of the chain reaction by dropping one of the either golf balls or ping pong balls, and it drops into the other balls. They are just standing in the top of the mousetrap, and as you can see and as you can imagine, all the balls are going to be flying out because all the balls are going to set up a new reaction when they hit a new mousetrap, and so on and so on. So that's exactly how it happens when you have nuclear fission, okay? Now, because I told you I was not going to go on the basics, I'm actually going to tell you about the energy released and the binding energy. And if you do not know what binding energy is, go on my previous video called Binding Energy. Okay? So, the energy that is released during the fission event is going to be the same as the change in the binding energy. Okay? Because remember that we spoke about changes in mass and energy and all that stuff. So the binding energy of each of the nucleons is going to increase as the result of the fission. So whenever I have fission, binding energy increases. And the explanation why is coming just below. So when you have fission, the fragments, which both have a positive charge because they are made of neutrons and protons, so overall they are positively charged, they are going to repel each other with a certain force. And this force needs to overcome the strong nuclear force that tries to hold the nucleons together in a nucleus. So the fragment nuclei and the fission neutrons are going to gain kinetic energy, and since the fragments are now going to be smaller, these fragments are going to be more tightly bonded together than in the original nucleus. So that means that they have a higher binding energy because it's going to be harder for me to separate them further. Okay, so they have a higher binding energy than the original nucleus, and therefore they are more stable than the original nucleus. Okay, I think that makes sense. This one makes sense. The other one is going to be the hard one for you, I think. Now, a really quick exercise just to make sure that we know how to do these fission reactions. So I say that I have uranium-235 is going to split into barium and krypton, and 2 neutrons are released. So you just need to figure out which numbers are going to show there, okay? So if I have a neutron, then I have 1 for mass number, and it has no protons, so it has 0. So because this is going to be just like a mathematical equation where the numbers before need to match the numbers after, then it means that barium, looking at the other numbers and knowing how many neutrons that I have, that they say there's 2, needs to be 144. And then krypton needs to have an atomic number of 36, okay? 56 is the other one. Because I have 2 neutrons that have mass number of 1, atomic number of 0. So this matches because 2 times 1, 2 plus 90 plus 144 gives me 235, 236 because I have plus a neutron, and 92 plus 0, so 92 is equal to having 56 plus 36, okay? Plus we have energy released. And now the energy that is going to be released, as you know, can be calculated using E equals mc squared. Again, I have a video that talks about this. I think it's 2 videos below or above. So if you go on the playlist, it's maybe 2 videos above. So the energy release is going to be the change in mass times the speed squared, okay, where the speed is the speed of light. And delta m, as I told you, is the difference in the total mass before and after the event, okay? So the mass difference would be the mass of the nucleus of uranium-235, okay, you shouldn't say 238, minus the mass of the barium, 144, minus the mass of the krypton, minus the mass of the neutron, okay? So that will be the difference in the mass, okay, that you use, and you input in the equation, and then you get the energy that is released, okay? Again, if you don't quite know what I'm talking about, go, I believe it's 2 videos below, or above actually, something to do with changes. I don't remember the name of the video, to be honest. Let me see if I can find it here. It should say something like energy in mass, okay? All right, nuclear fusion. So the one where you have two smaller nuclei and they fuse together to form a larger one. So this takes place, as I told you, when I have the smaller nuclei. They are at high speeds and they combine to form a bigger nucleus. I will tell you why they need to be at high speeds. Now, when the two nuclei combined, the individual nucleons become even more tightly bonded together. So they become even more stable than before because I'm fusing them together. So that means that also for nuclear fusion, the binding energy per nucleon is going to be greater than the original one, okay? Because now my nucleons are even more trapped in the nucleus than they were before. And again, the energy released during the fusion event is going to be equal to the increase in binding energy. So basically, I have an increasing binding energy both for fusion and fission. The reasons why are different, okay? One is because I have smaller nuclei in the fission event, and therefore they are held together through the strong nuclear force better than when it's a very large nuclei. Therefore they are more stable and they have a higher binding energy. In nuclear fusion is because when I fuse them together, I actually required so much velocity, so much energy, so I needed so much velocity to bind them together that they actually more tightly compact than before, and therefore the binding energy is going to be increased as well, okay? Now, why do I need high speeds? Just think about it. I have two nucleus, right? Nucleus, again, they are made of neutrons and protons. So overall, I have two positive charges or two positive stuff, or stuff that is positively charged. So opposite charges, they attract, but similar charges, same type of charges, they repel. So what happens is they actually try to repel each other. The nucleus try to repel each other. So I need a very high speed to get nuclear fusion because it needs to overcome the electrostatic repulsion between the two positive nuclei so they can come close together enough and then interact through the strong nuclear force, which again is in some of my videos, right in the first playlist. The strong nuclear force is responsible for getting the nucleons attached together in the nucleus, okay? So that's why I need high speeds. Another quick exercise. Let's just do these reactions, okay? So the fusion of two protons produce a nucleus of deuterium, the isotope 2,1 of hydrogen, a beta plus particle, and a neutrino. So I have two protons, so here we go, proton number 1 and proton number 2. So proton, the atomic number is the number of protons, so it's 1, 1. Mass number is the atomic number plus the number of neutrons. So because I have no neutrons there, it's still 1, 1. It gives me the isotope, deuterium, here it is. It gives me a beta plus particle, here it is. And it gives me a neutrino, which is right here, okay? Now, does it make sense? 0 plus 0 plus 2 gives me 2. 1 plus 1 gives me 2. That makes sense? Does it make sense here? 1 plus 1 gives me 2. 1 plus 1 gives me 2. This is 0. So it makes sense. It matches. I know my reaction is right. Always do that in your exercises. Exercise 2. The fusion of a proton and the deuterium nucleus, this one, gives the nucleus of the helium isotope 3,2 and gives me 5.5 mega electron volts of energy. So again, proton. I'm going, actually starts with deuterium. So 2,1 hydrogen plus a proton 1,1 because again, mass number 1, atomic number 1. In the deuterium, I forgot to tell you, so mass number 1 because it has 1 proton and then it has 1 neutron as well. So 1 proton plus 1 neutron gives me a mass number of 2. And this gives me helium 3,2. Does it make sense? 2 plus 1 equals 3. It makes sense. 2 is equal to 1 plus 1, so it makes sense. Question 3. The fusion of two nuclei of the helium isotope 3,2 produces a nucleus of the helium isotope 4,2 2 protons, and 12.9 megavolts, mega electron volts of energy. So helium 3,2 plus helium 3,2 gives me helium 4,2 and 2 times a proton of 1,1. Let's see if it makes sense. 3 plus 3 gives me 6. So 4 plus 2 times 1. So 4 plus 2 gives me 6. It makes sense. 2 plus 2 gives me 4. And here, 2 plus 2 times 1. 2 gives me 4. So it makes sense. In each case, the energy released in the reaction may be calculated using E equals mc squared in the form of Q equals delta M, the mass difference, times c squared. Well, where, again, delta M is the difference between the total mass before and after the event. So this is really easy stuff. Now, let me just give you as a note, fusion in stars. So we have nuclear power stations which use fission. Now fusion needs, as you know, a lot of energy or a lot of velocity for my nucleus, right? 9 nuclei actually. So I can only get this energy or this velocity if I get a lot of heat and pressure. Only then I can get 2 smaller nuclei to go around so fast that they can actually fuse with each other. So naturally, fusion happens in stars, okay? So this is how stars keep alive or keep, living, if I can say this way. So when you have a star that is a main sequence star, it means that the star is stable. So it means that the amount of force that is trying to collapse the star due to the gravity of all the particles that make up the star is just about balanced by the pressure outwards, and this pressure is due to the heat energy. Now this pressure, I get it from nuclear fusion. So from fusing helium to hydrogen to helium, and then I get helium to carbon, carbon to oxygen, oxygen to silica, silica to magnesium actually, and then it goes to iron if I'm not wrong. And then when I get to iron, this is going over my most stable nuclei. So fusion, instead of releasing energy, needs energy, and that's where the star cannot balance anymore the force of gravity with pressure because it doesn't have heat anymore, and that's where it dies, okay? So this is how a star looks like at the end stages of their life. They did the hydrogen to helium fusion, helium to carbon and oxygen, carbon to oxygen, sodium, neon, and magnesium, neon to oxygen and magnesium, oxygen to silicon, sulfur, phosphorus, silicon to iron, and then when I get to iron, then it's not going to release energy anymore, and that's where the star stops having this force in terms of pressure to balance out the gravity, and that's when the star collapses and dies. This is for large stars, and then they can have a black hole or a neutron star depending on the initial mass of the star. Stars like the sun, for example, they do hydrogen to helium, helium to carbon, but then they don't have enough heat and pressure to do more fusion, so they die out slowly into a white dwarf. There is already a video about the life and death of stars. So look, I think that's the name actually of the video, Life and Death of Stars, or is within one of my astrophysics videos. So take a look at it, okay, as well, if you don't know or if you want to know more about the fusion in stars. And that's it. Fusion gives you way more energy than fission. So on Earth, we are actually trying to get nuclear power stations that actually use fusion instead of fission, because then we don't have the radioactive products to worry about. But that's going to be in another lesson, because for now I'm going to give you these exercises from AQA. These are not mine, these exercises, in case you want to pause the video and do them. And then if you want to know what are the right answers for the exercises, here they are, okay? So up to my next video, take care, be happy and healthy, and that's it. Bye!